Hello, everybody, and welcome. I'm just going to give everyone a minute or two to roll in, um, and and then we'll begin shortly talking about data querying basics powered by IOX. Apologies. So an hour has gone by. So we are ready to go ahead and just get started here. So in this office hours session, we will learn about how to query InfluxDB Cloud powered by IOX, which I will just refer to as InfluxDB Cloud for the rest of this office hour with SQL. So in this lesson, we'll just be learning about the topics related to SQL, and in another office hour, we'll be talking about some of the other sections. So really just the first bullet is what we'll be learning about: SQL introductions and language syntax, basic SQL queries, grouping with SQL, aggregators and selectors, and an intro to SQL subqueries. But before we begin, I just wanted to give a little context for how it's even possible that we can query InfluxDB with SQL. And that all has to do with InfluxDB's new storage engine, which is built on Rust, Apache Arrow, Apache Parquet, Data Fusion, and Aeroflight. So for those of you who don't know, Rust is a programming language, and it offers fine-grained memory control. And Apache Arrow is a framework for defining in-memory columnar data. Parquet is a column-oriented durable file format, and Data Fusion is an extensible query execution framework that's also written in Rust, and it uses Apache Arrow as its in-memory format. And last but not least, Aeroflight is a new general-purpose client-server framework that's used to simplify high-performance transports of large data sets over network interfaces, and we take advantage of Flight SQL, um, which enables that transport as well through querying through SQL. So for this office hour today, we'll use the air sample dataset to understand how to query data with InfluxDB Cloud. And the air sensor dataset has the following schema. So it has one measurement, air sensors, three fields, carbon monoxide, humidity, and temperature, one tag, sensor ID, with 8 tag values, sensor ID or TML0, 100 through 0101, all the way up to 0203. And before we can query with SQL, we first need to load the data set. So the way that I recommend loading the data set is by navigating to the buckets page and then creating a new bucket entitled Air Sensors. Click the Add Data button and then write the data with line protocol. And if you visit that URL, you can actually just copy all of the line protocol directly and enter it manually. But I do want you to note that the timestamps will be different from the ones in that link, because that link is constantly updating to have the newest data. So that data will probably only be no more really than an hour old. Pardon me one second. Okay, so the way that we create a bucket, just for visualization, is we go into the UI and under the load data page, which you can identify from the left-hand navigation with a little line and an arrow pointing up. We'll send you to the load data page, and then you can click the button that says create bucket on the right-hand side that's kind of grayed out right now. And then you can go ahead and create a bucket, name it, and assign a data retention policy, how long you want to keep that data for, and then hit create. And then once you've actually created the bucket, you'll see it listed, and on the right side name of the bucket, you can see an option to add to data. You click line protocol, and you're good to go. So once you've entered it, you should get a confirmation that all of your data has successfully been written. And that's what that looks like. So now we're actually ready to start exploring our data and querying with SQL. So this is what the Data Explorer now looks like. It allows you to build SQL queries instead of Flex queries. And basically, you can use a drop-down window to select your bucket and your air sensors and go ahead and then use a SQL sync. This can be on or toggled on or off if you want to use the builder to create your SQL query. And then you can go ahead and select run and you'll see all your results here. And you can navigate between a table and a graph to see the results in both format, which is basically like the equivalent of the raw data view and um, the actual visualization. So now that we understand how to do that, oh, also worth noting too that if you press command /, you can comment out any of your SQL code as well. So that's useful to know about. And so now that we have like a brief understanding of the UI, I just wanted to kind of go into just a little bit in a little bit more detail. So essentially, this left-hand panel right here is where you actually can not only create your SQL queries, but you can also now save and select scripts. So you can create a new script, save the script, open existing scripts. This is a huge, like, long-standing feature that people are really excited about. Um, and then in the middle panels where you actually write your own SQL or use the SQL sync. And then on the right-hand panel is where you can, oh, excuse me, where you can create customizations for your time series visualizations. So now let's talk about how we can actually explore our schema. You can explore it in the UI like we just did, but you can also use uh, the following functions to explore your data. So you can use show tables and show columns and measurement. So this is what show columns and measurement would return. It gives you all of the column names, all the different data types of those columns, whether or not it's nullable, and the table that it comes from. So a big takeaway here is that, traditionally with InfluxDB, we think of measurements and tags and fields. But now that we're querying with SQL in InfluxDB Cloud powered by IOX, we should really be equating measurements to tables and fields and tags as just columns. And that's how we should be thinking about them because that's the world of SQL. And that's how we're going to be querying with them as well. So they're essentially equivalent. So let's actually go into a SQL introduction and language syntax now. So some of the key takeaways here are that you can query with SQL and InfluxDB Cloud. You can take advantage of the following documentation, which I'll share in a little bit. And at the end of this, I'll post a comment with all the documentation that I recommend checking out. Use the select clause to specify tags and fields from the data that you want to retrieve. Use the from clause to specify which measurement or table, they're equivalent, that you want to get your data from, and use the where clause to apply conditions or criteria to the column values that must meet whatever conditions that you specify in order to return the results. So I'll talk a bit about documentation that I would use for, really learning all the SQL that is available with InfluxDB Cloud, but I'm posting it in the comment section right now so that you can go ahead and take a look at all of these links. These are all the ones that I'll mention throughout this office hour. Just worth having, as a reference as you continue to play around with SQL and InfluxDB. So this is what the most basic kind of single SQL syntax looks like. And we've talked about this a little bit. Traditionally you'd say select my columns from a table where we meet certain conditions. And in InfluxDB, we want to think about columns as being tags and fields, measurements being tables. And that's kind of the start and end of it. So our SQL will look the same thing. We just have to make that one kind of mental shift. But it's also important to know that you have double quotes are used for identifiers like column names, and single quotes are used for string literals. And it's also worth being aware that in SQL, the syntax order and the process order are not going to be the same. So that's something that you have to be aware of when you're writing SQL. And sometimes you have to use subqueries to change the process order to get the result that you want. But in general, and there are exceptions to this list, it's just kind of a general order, process order. This is the way that data is processed as part of the query or received. So first the select, then any as clauses, then from, then where, then in, not, exists, exists, and not exists, then group by or having, order by, union, join, and last but not least, limit. So it's just important to recognize that the process order doesn't match the syntax order, and that this is generally kind of what the process order looks like. So the simplest SQL query would look like select all from error sensors. This would return all of the data from your table or measurement. And so now let's go into some basics in SQL queries. So some of the key takeaways for this subsection are relatively the same. We're going to use select from and where to build some of these basic queries. And this is the documentation that I would follow for this section, which again, I've put in the comments, so go check it out. So the first question I might ask is, how do I return all the data for the last 10 minutes? Well, the way that I would do it is I'd say select star from error sensors, where time is greater than now minus an interval of 10 minutes. And this is just, if you see differences between like the SQL that you're aware of versus this one, this is just because this is the SQL that is part of the Aeroflight SQL library. So it's just this implementation of it. And so if we do that, we could see our data is in fact being returned for the last 10 minutes. Then we might have a question, let's specify, you know, specific temperature data. How do we do that? In this case, we could select for just one column, just the temperature from air sensors, in which case that's what we would return as just the temperature. And we might also ask ourselves, how do we limit our results to just the first 5 temperature data points from air sensors? And in this case, we would just use that limit clause with limit 5 to say we just want to return the top 5. And it's also worth noting too that, hold on, where did it go? You can see the number of rows that are returned right here. So that can help you verify that your results are as you expect. And now we might ask, how do I return all the temperature values that are greater than 72? Well, this is where the where clause comes in. We can use it to specify that we want temperature values that are greater than the value we're looking for. And in this case too, we also decide to select for temperature, time, and sensor ID, just because just offering the temperature column like we were doing before doesn't really provide a lot of context or meaning. So we decided to add more columns. This is how you would select for specific time ranges. You could use the where clause and specify one timestamp and then specifying the type and saying that you want the time to be greater than or equal to this timestamp and less than or equal to now, for example. And we might also select for a specific sensor ID as well to narrow the results for one sensor ID. And so, this is what we'd return. We'd notice that all of our data is in fact from a single sensor ID, and that our timestamp is just always going to be greater than or equal to 10 minutes from then, or from that specific timestamp. Okay. That's not really an important note. Basically, just be aware that the timestamps that we're looking at here are going to be different than the ones that you have if you're importing new data. So now let's talk about some basic aggregations. They would include things like count, average, sum, min, and max. So one of the first things that a lot of people like to do when they're querying with SQL is to ask, what is the min, max, and average temperature for a particular sensor? Let's say sensor TML0 100. And in that case, we would say we want to select the min temperature, and then we can use as to rename that column as min underscore temp. Max temperature, we'll rename it as well. Average temperature as average underscore temperature to rename that column as well, from our same table, air sensors, where time is greater than this one time range and less than now. And we will also, filter our results for getting data just from a particular sensor ID. And this is the result that we get. We can see that we have an average temperature, max temperature, and min temperature. And so we have gotten what we expect. And then it's worth noting too that now you don't have to include time intervals in your InfluxDB queries. This is a really long time request. In the past, users always had to specify a time range to query InfluxDB with InfluxQL, or later with flux. And so now you can return global values across all of your data without having to do that. And it's extremely efficient and fast. So this is a huge win for people that needing to do that, especially people that maybe have event data and they don't know when the last value of their data was. So they don't really know what timestamps to provide. Now they can just say last and gather that event data, especially if it's sparse, for example. And we can also use the selector underscore min and selector underscore max functions, which are even more performant, but they return the data in an array. So it's just a little bit of a different format, but also helpful because you can then reuse some of those values if you want to perform additional calculations with them with SQL. So now let's talk about having. So we can use having to aggregate a result that meets a certain condition, an aggregated result. So how do I return the mean temperature values that are greater than 72? So we can say select average temperature as mean temperature, comma sensor ID from air sensors, group by air sensors, having a mean temperature greater than 72. So the having clause places conditions on the result created by aggregating operations on groups. And the having clause must follow the group by clause and proceed any order by clause. Um, so, and yeah, so there we can go. There we go. We see the results. We are getting our mean temperature for each sensor ID returned to us. And we're doing that where mean temperature is greater than 72. And we're using the having clause instead. So now we're ready to talk about subqueries. So basic subqueries will oftentimes use exists, not exists, in, and not in. And we will use the in clause to select for data in multiple sensors rather than use multiple conditions in a where clause. So essentially, if we ask the question, what is the maximum temperature for sensors 100 through 102? And I guess this isn't technically a subquery, but we are going to just talk about using the in clause first because that we also often can use those in subqueries. So if the answer to that question is we'll select the max temperature and sensor ID from air sensors where sensor ID equals this sensor or this sensor or this sensor, and then we group by sensor ID, or we can just use the in clause instead and just say in parentheses all the sensor IDs that we want. So it's just kind of a simpler, more compact syntax essentially. And when we do that, we can in fact see that we get the max temperature value for the sensor IDs that we selected. So that leads us to another question, because you might be wondering, how do I then graph temperature and humidity data, for example, two fields simultaneously? And the answer is in the Data Explorer, you can't. So the Data Explorer is really just meant for exploring your data. It's not meant to be a replacement for your data visualization tools. And instead, we encourage you to use Grafana, Superset, Tower BI, Tableau, or Power BI to visualize your data. Because there's already interoperability with Grafana and Superset right now, and more is coming with Tableau and Power BI shortly. And so we encourage you to use the purpose-built tools that are meant for that instead. Oh, and let me go ahead and actually share some of the links about visualizing in Grafana and Superset so that you have those available to you and you can go ahead and use those as you want. Okay, so now let's talk about grouping. So some of the key takeaways here is that anytime you use aggregate functions like average, min, max, count, etc., you have to use a group by. We use group by to group by one or more field or tag columns, and you're required to use group by before a having clause. We talked about that already. But if you want to perform essentially downsampling, you're going to want to use the date bin function to group data by time intervals. I think sometimes people think, oh, I should use group by time to create buckets of time intervals and then apply a max over that or whatever your downsampling goals are. But you have a special function for that instead. So that's the kind of one of the main takeaways there. So yeah, follow the group by documentation that I linked in the comments. Um, how do I aggregate across a series? So if you wanted to find the mean carbon monoxide value for each sensor, you would say select average carbon monoxide as mean carbon monoxide. You'd also select that sensor ID from air sensors and then group by sensor ID. So we did the same thing with temperatures, so we should be pretty familiar with it. Here's what our results look like. So if we instead want to calculate the average temperature for each sensor over 1 minute intervals, we instead will use the date bin function. So we select our sensor ID and then we're going to select our time, which has now been placed into date bins or little intervals of time. And we specify the interval that we want that duration to be, that bucket to be, how big we want that to be. We specify where we're getting our timestamp value from, time, and then we specify the timestamp that we want to start creating our date bins from. And then we'll rename those newly calculated date bins as our new column, which is time. We'll just rename it the same thing. And then we'll select average temperature as mean temp. And we'll use the where clause to specify the time range that we want to get our data from. And we'll group by time and sensor ID, just so that we can then see our data together. So we can see we have mean temperature values for each one of our sensor IDs, and we'll notice that we have now our timestamps are all on these minute values. And we order by to change the order of results, because when we go back, this is fairly messy, just because there's not really an ascending order in terms of time in terms of sensor ID or time, and so it would be helpful if we could see our results a little bit better. So we can use order by to change the order of our results, and you can either order by the name of the column or the position of the column or what we selected in the select clause. So if we wanted to order by sensor ID, we would say order by 1 or sensor ID, or we can say let's order by time, or the second thing that we selected for. So order by 2. And we can see now that we have, in fact, done so. So we have all of our buckets or our date bins for every sensor ID for the first date bin presented to us first. Sorry, that was a duplicate slide. Okay, so last but not least, let's talk about some aggregators, selectors, and time functions. So we talked about these a little bit already. So here's some of the general aggregate functions. And we've already talked about, selecting a min temperature value and a max temperature value and an average temperature value. But one thing I wanted to note is that if you are using any of these general aggregators and you're not using a selector like last or first, it's important to be aware that since you're aggregating over a bunch of data, there won't be a timestamp associated with those functions. So you can't select for time because it just doesn't exist. There's not a time for like the average value. There is a time for the min value and the max value, but not the average. So if you're selecting for all of those, you can't also select for time. But also, it's worth noting that there are a bunch of other aggregate functions that are available to you as well. Here's some statistical aggregate functions, things like correlation, variance, standard deviation, etc. So now we might also want to figure out how do I calculate the correlation between humidity and temperature across all sensors. So you could just use that statistical aggregate function directly and provide the two columns that you want to find the correlation between. And then we can return our correlation value. We can also use approximate aggregate functions. So these use algorithms for increased performance to provide really strong estimates of the values. And they're basically just aliases of other aggregate functions that use less memory. So it's worth being aware of if you are looking to, I don't know, calculate the median value across a absolutely massive data set. There's also these selector functions. I talked briefly about them or introduced them earlier today when I was talking about taking the global, max value across all of your data. And selector functions work just like aggregate functions, but they return a JSON struct that contains both the value and, sorry, I think I said array, but a JSON struct of the value and the timestamp. And this is especially helpful if you then want to use that value in another calculation as a part of a subquery. And we'll maybe talk about that in a little bit, but the JSON struct that it returns looks like this. So if I were to, calculate, I don't know, maybe that's like the max temperature value for a particular sensor, and it gives me the actual value with the timestamp. So if I wanted to use the selector min function, I could do the following. I could say select selector min humidity comma time, and then specify that I want to, from that selector function, get the value. And then I'll put that in a column called min underscore temp. And I'll do the same thing for the time. And then we'll actually just get that 1 point returned to us, and we can choose to graph it if we want as well. So now we're ready to talk about some subqueries, and this will be the final section for this office hour today. So some of the key takeaways here is that we use subqueries typically to build more sophisticated queries and make calculations, but we also use subqueries just to apply functions in different processing order. So the first question might be like, how do I limit my result first and then order the temperature values? Um, So we would have to use a select for a subquery for this. So we're going to need to change the processing order of our SQL functions in order to actually calculate this. So we'd first say that whenever we're reading subqueries, we always want to find the innermost subquery like a nesting doll and then work our way outwards. So we would first look at the innermost subquery, and we would say, we want to select from air sensors and limit 5. So first we want to limit our result set to 5. And then let's order by temperature values. So that's how we can do that. And it would also probably have been more useful to illustrate this point if we had included sensor ID as well, so that we could like really verify that we are in fact first limiting our result set to the first 5 values that we have, uh, and then ordering by temperature. Um, but we can just trust that that's what we expect. So we also typically use subqueries to perform things like math across measurements. So you might have the following question: how do I find the correlation between two fields across two different measurements? For this example, let's just imagine that we have a second measurement or table called air sensors 2, and it contains things like the flow rate. And so let's pretend that we want to find the correlation between the temperature value from our data that we have already and the flow rate from this air sensors 2 table. So what we'd be doing here is essentially first, we want to select the correlation between our first table dot temperature and our second table dot flow rate. And we're going to be finding that correlation from our subquery. And so we have to select for everything that we want to query for. And in order to calculate a correlation across all these values, we have to first join these values together. And that's what we're doing in this subquery. So we'll select for our first table dot temperature, first table dot time, first table dot sensor ID, and first table dot flow rate. As well as maybe our second table.time, which I forgot to include here. And then we'll select that from air sensors as our first table, and we'll join on air sensors 2 as second table. And we can join our values on, on our second table.time and first table.time. And maybe we also want to join them on our sensor IDs as well. So once we've joined our data together, then when we have both, a temperature column and a flow rate column available to us, so we can go ahead and find the correlation between both of those. And I wanted to just share an example of a sophisticated subquery as well, so that we can understand kind of the power of subqueries. So the example in this example, the goal is to essentially just calculate the slope or the rate of change of our carbon monoxide levels and our temperature values. So in order to read this subquery, let's start from the innermost portion of our subquery. So basically what we're doing here is we're firstly, taking our time values and we're casting those as integer values in nanoseconds. And then we are also lagging that value by one position or one row. So that then we can subtract it from the original value, so we can find a difference or a delta between those two timestamps, and we'll set that as time. And we'll do the same thing for our temperature values and our carbon monoxide values, but we won't cast those as integers because they are already floats. So we can go ahead and subtract them already. And then once we've, created our carbon monoxide delta values and our temperature delta values, or sorry, this should either say delta T. No, this is delta TNS. My apologies. I got ahead of myself. And essentially, um, that means that then we can go ahead and actually calculate uh, now the slope by doing the change in the rise over the change in the run. And we multiply by 1 billion to change that units from nanoseconds to seconds. So it just has a little bit more meaning. And then we can, change that rate as carbon monoxide rate and also as our temperature rate. So we provide some more meaningful clues about what we're actually calculating, what those columns represent. So that's all that I want to cover today. Thank you so much for joining this office hour. If you have any questions, please put them in the comments and I'm happy to talk to you about them. And I encourage you to join us every Wednesday for office hours. We have a wide variety of topics, and you can even go to YouTube and see what's coming up. So yeah, I'll stick around for a few minutes to see if anyone has any additional questions. And thank you so much for joining. Okay, since there are no questions that I can see, I'm gonna go ahead and sign off. Thank you so much for coming. Bye, everyone.